Hello and welcome to Stars, Cells, and God. My name is Hugh Ross, and today I'm joined by Jeff Zweerink, another astrophysicist on staff here at Reasons to Believe, and he's going to be discussing Earth's geodynamo. I'm going to be talking about the most distant galaxy discovered in our universe. I'm all excited about this geodynamo. We've both been writing about this for a few years, so tell us what the latest is.
Well, just to kind of set the stage, as I've heard how typically evolution is described, and I put it in that context because often the way it's presented is, there's just things that happen on the Earth, life responds to it, and this is what you get. And one of the things that I've recognized just as I've looked at and studied things is that it's a little bit more complicated picture than that, because it's not just that, okay, things happen on Earth and life adjusts to that. What you actually have is very often the life is dramatically changing the dynamics of the Earth. So, you go back to the early Earth, there's virtually no oxygen in the atmosphere. And for most of Earth's history, there's no oxygen in the Earth's atmosphere. About 2.5 billion years ago, you start getting oxygen. And then more recently, the last 500 million years, it's increased up to something like 20% of Earth's atmosphere. So life is dramatically changing the dynamics of Earth. But you look at the sun. I mean, you've written about this for decades, where the sun is growing in intensity steadily. It started off much brighter, dimmed down, and now is getting much brighter over time as time goes on. That this is a change that could catastrophically impact the Earth. You look at the Earth starts covered in liquid water, but yet still hostile to life, and you've got continents that grow over the last 4.5 billion years, and so now continents dominate about 30% of Earth's surface, and the growth of continents cause changes that could very easily make Earth uninhabitable. The atmosphere changes, and so what I've noticed is that instead of it being there's this one thing and life is just responding, there seems to be this complex interplay between the sun's getting brighter and continents are forming and the atmosphere is being removed of methane and oxygen's coming into the atmosphere and life comes on. And it's this complex interplay. And the one kind of stable feature through all of that is that Earth's global temperature has stayed within about a 20 degrees Celsius window for 4.5 billion years. And that's just a phenomenal thing for me to comprehend and appreciate, because there are so many things that could have dramatically changed that. And if Earth gets too far outside that, it gets too hot or too cold, it becomes uninhabitable. And so, rather than Earth changes, life adapts, I see this more complex interplay, and that is what fascinates me about some of this latest research into Earth's magnetic field. Because again, we think, okay, Earth's got a magnetic field, we can measure it, we know our direction, we use it today almost as an afterthought. Most of us aren't aware of it, but we know it's there, and it plays a very critical role in keeping the sun from sputtering away the atmosphere, because it deflects the cosmic rays around, makes the aurora borealis and aurora australis that you can go take expeditions to see and are cool and beautiful and fascinating.
And protects us from cosmic radiation.
Well, and that's what's causing that, is that it's funneling that up to the poles. And so it makes these cool displays. But even beyond that, as geologists have known that, okay, if the Earth has a magnetic field, as rocks cool, they're going to record that magnetic field. And so we've been able to understand something about how the Earth's magnetic field works by studying these rocks, and we recognize that there's an interior structure to Earth. We've got a crust, we've got a mantle, we've got a core down at the center, kind of those 3 or 4 basic structures. And as these plates float around on the crust, on the mantle, they move around. And what generates the magnetic field is this liquid core where it's made mostly of iron, so that circulates around, and you got moving metals that generates magnetic fields, or because metals are made of charges, they've got magnetic fields. That's where the Earth's geodynamo comes up. But by studying the rocks, what we find is that this magnetic field actually reverses. So what we see is north and south, it'll change to south and north. irregularly. Typically, the transitions happen on the order of a few thousand years. So in geologic history, that's kind of a cosmic blip. But, for Earth or for humans, that would be kind of a bigger thing. But what's interesting is that over the last, 10, 15, 20 years, not only have we been able to start studying just the direction of the magnetic field, but actually the strength of it.
Right.
And that's a much harder challenge. And part of why that's interesting is because as people were looking into the Ediacaran period, which is, about 500 or 630 million years ago to 550 million years ago, that time frame, as they were looking at the magnetic fields and the rocks of that time, they were just getting all sorts of weird directions. It was hard to get a coherent picture out of that. And by looking just at the directions, they couldn't get an understanding. And so people were saying, all right, what's causing all of this? Maybe, how bizarre this data is that they're saying, well, maybe what we have is that Earth's magnetic field during this time was just very rapidly changing directions. It'd point over there, point over there. But in order to explain the directions of the field or that we were measuring in the rocks, this would have to be happening at far faster rates than you could sustain based on the structure of the Earth.
Well, what I've been reading, Jeff, is that what's happening is it goes from a dipole to a multipole. And when you got a multipole, you got multiple directions.
That could be going on in there.
Yeah.
I'm just, this is, as people were looking at that saying, wow, it could be going all sorts of different directions.
Right.
They thought, well, maybe not only was there a north-south pole, but there might be an equatorial pole, an east-west pole, and that's what we're recording in here.
And maybe many other
Very
poles.
bizarre data.
Yeah, right.
Turns out what they were able to do eventually is to go in and show, as they begin to, or they developed techniques that allowed them to now look at the strength of the magnetic field,
Right.
not just the direction.
Right.
And that's a very challenging thing because the direction is just recorded. You got magnetic grains, that's going to tell you the direction. But to get the strength, you need more. And it turns out there's only a few kinds of rocks actually allow you to record the strength, because anytime you go take it into the lab, the manipulations you do to measure the magnetic field or the orientations often will destroy any sort of information about this, or disturb any sort of information about the strength. But they were able to find certain kinds of rocks that have grains that are 500 to maybe 50 to 500 nanometers in size. So they're single grains. So the magnetic field is recorded directionally very well in there. But if you have rocks that have a whole bunch of those grain sizes, now the ensemble of how those align will give you information about the strength of the magnetic field. And as they found more and more of these rocks, what they were finding is that during this period where the magnetic field seemed to be all over the map, Earth's magnetic field was more than 10 times less than what it is today.
Right.
And so you've got this place where the Earth's magnetic field is just decaying, which is remarkable because, again, during the transition, it drops off. So as it's going from north-south to south-north, it's going to drop off for a few thousand years. But what they were finding in this period is that for this time span of about 10 million years, it dropped down to less than 10% of its current value. And it seemed to stay that way over the whole time. They found evidence for this not only in Laurentia, which is kind of up in the Quebec region. They were measuring some rocks up there. They found evidence for this really low magnetic field over in Ukraine, which is a different continent at the time, Baltica. They found evidence for this. They found it in Gondwana, down in South America. I'm drawing a blank. I want to say Brazil, but that's not where it was. And so it's not just a few places, but it seems like kind of across the globe, we're seeing this dramatic decrease. And so it's kind of just, there's part of me that I just find really the ingenuity of people to figure out how to measure, or scientists to figuring out how to determine things is really remarkable, because you're stuck with whatever the data is here on the Earth. How do we now, what sorts of things do we look for to find the information we need to adequately constrain things? And that we found there are certain kinds of rocks. We've been able to find those rocks, analyze those rocks, and find that for a period during the Ediacaran of about 26 million years is the number they put on it, the magnetic field strength was as much as 10 times, if not more. Some they found up to 30 times weaker than today's magnetic field. And that has big implications. I think we were talking before the show that if you get a drop of the magnetic field for a few 100 million years like that, you're going to cause life to go extinct on the Earth, or at least it's going to have dramatic consequences. And so, what is interesting, what I find interesting, and the article that I was reading found interesting. It was in a Physics Today, and it was titled "Earth's Magnetic Dipole Collapses and Life Explodes." And it's that life explodes part that I find interesting, because this happened right during the Ediacaran period, which is where you have the tail end of that is where you have the Avalon explosion. And so what people were arguing, and there's maybe what's going on here, is that as the Earth's magnetic field decays, you get more cosmic radiation coming into the Earth. That may create, various processes may create more ultraviolet radiation that gets down to the surface of the Earth, various things. And so that may actually drive the mutation, or that would cause the mutations that drive this explosion of life. Now, one challenge in all of those scenarios is that you're dealing with life on Earth at the time, and all of this life was in the oceans.
Yeah, and if it's in the oceans, it's protected.
Exactly. But there's this intriguing connection of what's going on here. Why is it that right when the Earth's magnetic field is decaying and dropping to this very low, small value, why do you have this beginning of this explosion of new kinds of life in there? And, I'll get to it in just a minute here. Not too long after this, the magnetic field rises back up, and shortly after that, the Cambrian explosion happens.
That's right. Yeah.
And so why that happens, though, there's another field of research when you come into it from, rather than looking at just how is stuff moving on the surface of the Earth, what's going on in the interior structure of the Earth. And what they're finding, or as they were able to make intensity measurements of the intensity of the magnetic field, they showed that for the last roughly 3.5 billion years, the Earth's magnetic field had been slowly decaying,
right,
and it was approaching this kind of weakest place where it could be right around the Ediacaran period. But shortly thereafterward,
it jumps
dramatically increased,
right.
And that seems to correspond to the time in, or the explanation for that is that in the Earth's core, it's not just crust, mantle, core, that there's actually structure to that. And inside the core, it looks like, or that there's actually a outer core and an inner core, because as the Earth continued to cool and heat is being radiated away from the iron, its conductivity was higher than we thought, more heat's flowing out, that it actually moves from a liquid to a solid state. It starts to crystallize. And when it does that, maybe a little bit counterintuitive, because you throw water in the freezer, and when it gets cold, it turns into ice. So we tend to associate crystallization with being cold. But in doing that, it gives off a lot of heat, which drives heat back through the core, into the core mantle boundary, into the mantle. You get more convection, stirs up the activity in the core, regenerates the magnetic field. And now we're still living in that era where the core is crystallizing, generating this heat, driving the convection in the outer core, which generates this large magnetic field, which is pretty critical for life that now lives on the surface of the Earth, because it does it. Now you do have to protect the Earth from the cosmic radiation that would come in and hurt life. And so from the apologetic perspective, what I find fascinating in this is that as we talk about going out and finding extrasolar planets, it's like, okay, if we get water on there, we're going to have life on there. If it's just got, these few features, it's going to be a place where life can exist and
possibly exist.
Right. Well, you read the literature, scientific literature, and roughly 10% or 20% of stars have habitable planets, because 20% of stars have a planet in the region of the star, orbiting in the region of the star, where it could have a global temperature that sustains liquid water.
Yeah, that's assuming you have only one habitable zone.
Well, but even independent of the habitable zones, it just says where you've got a planet that's going to be where liquid water could exist, you can get liquid water.
Right.
But when we look at what's going on here on Earth, we see that it is a far more dramatic interplay of what's going on in the atmosphere, what's going on in the interior of the Earth, what's going on the surface of the Earth, what's going on with life on the Earth, what's going on with the sun. There's all of these factors at play in there. And it isn't just a simple, oh, you're this far away from the sun, you're going to have a habitable atmosphere because you're going to get liquid water, it's going to be the right temperature. And specifically, what I find fascinating about this, and I know you've written quite extensively about this, is that the Earth's magnetic field is decaying over time. 4.5 billion years is a long time for a planet to be around. It's decaying over time. And there's kind of the longstanding question, why did God wait so long? Okay, so if God created all the life on the Earth, why did he wait so long? I mean, couldn't he have created life earlier on? And I will say straight away, God can do whatever he chose. But given the laws of physics he chose for this universe and the way our solar system formed, if God had created humanity earlier, the planet wasn't prepared for it.
Right.
And in some sense, what you see here is that it took 3.5 billion years for the Earth's magnetic field to decay and for the crystallization in the iron core of the the iron inner part of the core to nucleate, which now drives a magnetic field which will be stable for the last 5.5 million years, which leads to all of the changes that ultimately allow humanity to be here. So part of the answer to why did it wait so long is, given the way the laws of physics are set up, Earth's not ready to support human life until today.
Well, we need all those microbes to put the oxygen in the atmosphere.
Exactly, yeah.
We need them to concentrate the metals from liquid or soluble to insoluble.
Mm-hmm.
So there's good reasons why you have 3 billion years of microbial life.
Mm-hmm.
Those are crucial to prepare the planet for megafauna and
that's that life is ultimately what is going to drive the oxygen in the atmosphere. Because if you get rid of that life, the Earth has no oxygen in the atmosphere. That's what drives
and you need
produces
the
all
deep
the oxygen
cycle to put the oxygen bursts into the atmosphere.
Well, I think that's something that I didn't appreciate until working here for a while, is that just getting oxygen in the atmosphere isn't quite the answer.
No.
Because that oxygen is oxygen is a very reactive element, and so it gets driven into minerals and rocks and other things, absorbed, put down. So you've got to fill up all of those sinks so that the oxygen can remain around and not get used up so quickly. And it requires a great abundance of life as well. And so, there's, as I look at this, the picture I see, from an engineering standpoint, you go, oh, that's kind of wasteful. Couldn't you have done this faster? Possibly. But I see a creator who is very generous, creating a lot or fashioning a planet where humanity can thrive and enjoy and grow and flourish, not just kind of minimally survive. I mean, you mentioned this number of times where there's a beauty and a fascination with being in creation. In fact, creation is so spectacular that people get so excited studying creation, we forget to worship the creator.
Yeah,
it's that abundance.
1, right? Now, what fascinates me about Earth's magnetic field is you have to have not just liquid iron in the core of the Earth, it has to be circulating. Mm-hmm. If it doesn't circulate, you don't get a dynamo, you don't get a magnetic field. And what's happening in the early part of Earth's history, you got the moon slowly spiraling away from the Earth. And because of the moon's tidal effects on the Earth, that circulates the liquid iron inside the Earth. Mm-hmm. But it's moving away. So it explains why the magnetic field slowly declines over the first 3 billion years of Earth's history.
Well, and beyond that, you're also just losing heat. I mean, it's not an infinite reservoir of heat. It's slowly getting cooler, too.
But what I find it really incredible, and this is the point I think that your paper's bringing out, is here's the moon spiraling away to a point where Earth's magnetic field could actually drop to a point where life can't survive. Mm-hmm. But at the moment where we're facing that risk factor, what happens? The core of the Earth cools enough that you get a solid core surrounded by a liquid core. And that solid core sets up a dynamic where you got heat flow coming from the inner core through the outer core to the mantle. That contributes to the circulation. You also got light elements inside the solid core that's being squeezed out by the fact that it's solidifying, and those light elements moving up through the mantle also contribute to the circulation. So just
I think that that's an interesting point to bring out, is that it's not just that the Earth's core is sitting there and it's hot, is that there's got to be something that drives the motion of that. You've got the tug and pull of Earth's moon, but another interesting side note they put in here is that you've got to have something that causes this liquid to move around. Right. And usually you have hot and cold. That causes it to move. So if the core or the inner core is a hotter temperature than the core mantle boundary, you're going to get motion of the metals in there. But it also seems like there may be, based on some of our studies, actually two different. Under the Pacific Ocean and the Atlantic Ocean, as you've got deep subduction going all the way down, that may actually generate a different thermochemical gradient, which would drive circulation in there. So this is not just, you've got a hot core. You actually need things that cause it to move around.
Contribute to the circulation, not just one. You need all three to keep the magnetic field strong enough to sustain life. But yeah, what fascinates me at the moment that the moon was no longer going to be able to sustain enough, enough circulation to keep the magnetic field strong enough, that's when the Earth's core begins to solidify. And to solidify in just the right way, basically to kickstart the circulation. And so it explains why you see this sudden jump in the magnetic field. And
it may even be more complicated than that, because it may be that one thing may not be adequate, because the paper even alluded to, it may well be that there's an inner core, and even within the inner core, there's an inner and outer core. And so, typically the first thing that happens is biggest and the next ones are smaller. So it wouldn't surprise me that this is two things about that. One, the inner core solidifying is the biggest impulse of heat that's going to drive that. There are others that are sustaining it, but it also may mean that there's a limit to how long this can happen, and we may be running up against that in the not too distant future, which again is very consistent with what Scripture describes. This isn't meant to be a permanent home.
It's not meant to be a permanent home. I think we've got a little bit of time.
I think so too.
Because where it's going to completely shut down is where the entire core becomes solid, which is what happened to the moon. It too had a liquid iron core, and it too had a magnetic field early on in its history. But being a smaller body, it cooled faster than the Earth, and so its liquid core became 100% solid. When that happened, the magnetic field went away. That's going to happen to the Earth.
Absolutely, yeah.
Fortunately, the inner core is growing by only 1 millimeter a year. So it's going to be a while before we actually have the entire core in solid form.
Right.
Nevertheless, as that core gets bigger and bigger, we do see a diminishing in the magnetic field. Fortunately, it's very slow, so we're okay for a while. But if we're looking forward to having humans here for 1 billion years, that may be a bit of wishful thinking.
This is one thing I find fascinating about studies like this, is that there are, you kind of point to Big Bang cosmology, Einstein developed theory of relativity. It's like, it looks like there's a beginning. There's times where it's just like, that even in the gross features, it points to what you see. There's an aspect of this where the more we know, the more it points out.
Yes.
Because, again, the general picture was, okay, we got water. Life seems to thrive wherever we can find it. As we begin to study creation, it seems like, life changes, it evolves, it seems to flourish everywhere, even extreme environments we didn't think. It's like life is robust, and wherever you get minimal conditions, it will show up. But this seems there's an aspect of this that as we dig into it more and more, yes, we find that Earth is incredibly well designed for life, and life shows up and it flourishes across places, and even places we didn't think it could survive, it flourishes. But as we know more and more, we see more and more of the details, and more of those details actually confirm that Earth works remarkably well to support life. and that there's going to be a definitive end to life on Earth. It just can't exist forever. I mean, we
Well,
talk about the core coming up here, but the sun's going to get too bright. Eventually, it's going to expand out. It may consume the Earth. I mean, I can give you at least 5 different independent scenarios where we know life on Earth is going to die.
yeah.
So the idea that we can just, hey, we're going to find a way, move on. The Earth, the universe is going to be diminished in its capacity.
Eventually, the protons all decay.
Exactly. Yeah,
That
exactly.
takes a while.
No, I can think of multiple ways where the universe might just be catastrophically die. But again, if I ask the question, what does Scripture describe of Earth and the universe? That as we've dug in and understood things more, it confirms that picture that there is an end date to life here on Earth. Now, is science saying it's going to be in a few thousand years when Jesus comes? No, it's not giving that level of detail. But it's clearly saying life is not going to go on here on Earth. It's questionable whether we'll ever be able to leave Earth or the solar system with our life. As easy as science fiction makes that sound, that may never, ever happen. It's just that challenging. And the Earth is incredibly robust in its capacity to support life. That's exactly what I would expect to find if I study Scripture. And as we study Earth and what we find here, that's exactly the picture we find. That, to me, is a powerful apologetic that the authors of Scripture knew what they were talking about, because there's stuff in there that isn't obvious to see based on what we can tell just by looking at creation without the scientific enterprise that we've developed in the last 400 or 500 years.
Yeah, what amazes me about this study, Jeff, is that at just the right time, when the moon is no longer able to sustain the magnetic field, we got the Earth's core solidifying. And moreover, we used to think that iron solidifies at a single temperature.
Mm-hmm.
We now know there's 2 kinds of iron, a cubic form of a solid iron and a hexagonal form, basically different crystals. But they solidify at 2 different temperatures that are separated by several hundred degrees. And so what we're now seeing in this Ediacaran and Cambrian explosion era, 575 to 530 million years ago, is that you have the magnetic field going down, as you mentioned, gradually going down, and then it has this sudden jump up. It weakens again and jumps up again. That's based on the fact that we're seeing the Earth's core solidify at 2 different temperatures. And so we see these 2 different expansions of the core. But what astounds me, it all happens with perfect timing, because you need oxygen in the atmosphere to be at a certain level to get the Ediacarian animals, about 8%. For the Cambrian, you need 10%. And that's all at the same time these magnetic phenomena are occurring that permits them to exist. So it's like the more we study this, the more complex it becomes and the more amazingly designed it becomes to make life possible here on Earth.
Yeah, I think, just kind of to wrap up, I've made this argument. I think I have an article on our website called The Great Symphony, or Earth's Great Symphony.
Yeah, I remember that one. It's a good article.
There's this idea that, okay, life and the Earth are just kind of meandering, mumbling through, and, oh, look what's happened. This is pretty spectacular. But as I look at it, I see this great, you've got all of the different instruments, all of the different factors working towards this common, producing this beautiful music that a symphony would, and the music being this great symphony of life on Earth. And that we're at a time where we can not only see it all, but enjoy not only the life, but the habitat where it is. It really is a spectacular creation we live in.
Yeah. And there's a lot more than just 64 players that make it all happen. Okay.
Right.
Well, thanks, Jeff. That's great. The paper I'm going to talk about just got published in Nature Astronomy, and it's about some measurements on what's known as the most distant galaxy ever discovered. And so this galaxy was discovered about a year ago. We talked about it at our James Webb Space Telescope workshop. It has a redshift of 14. So it's sitting at in fact, what's about this paper, they use the mid-infrared spectrometer on the James Webb Space Telescope to really get an accurate measure of its redshift, because they're saying it's approximately 14, Now they know exactly what the redshift is, 14.32.
Okay.
And that corresponds to a distance of 13.48 billion light years away from us. So
I think officially the way to say that is the light's been traveling to us for
13.48 billion
13.4.
years.
Because
So
talking about distance is a little more complicated because that
it
object
is.
is far farther away.
Right.
But I guess
At the epoch of the galaxy,
yes.
but not at the present epoch.
I appreciate that's the whole reason I bring this up is that there's this common thing. We use these terms and it's a little bit ambiguous what they mean. And
It
so
is, and like I tell my wife, is as an astronomer, I only know about the past.
Yeah.
Because all my data comes from the past.
Right.
I can't be held responsible for what's going on in the present. So
how well does that work out for you?
that doesn't work. But in astronomy, that's
Yes.
really true. We
No, it
have
is.
no idea what's going on in the present. As we look at stars and galaxies, we see them as they were when the light left those stars and galaxies.
Mhm.
In this case, we're looking at a galaxy when the light left it 13.48 billion years ago. Or to put
That's remarkable because that's getting like 300 to 400 million years after the Big Bang, which is incredible.
291.
291. Okay.
291 million years after the Big Bang. And so this definitively ranks as the most distant galaxy ever discovered.
Right.
Or probably a better term, a proto-galaxy. It's not a fully formed galaxy. We don't see fully formed galaxies until a redshift of about 5. But we do see emerging galaxies at much greater distances. But this is the most distant one yet.
Is a little bit of a detail on that because I thought that was part of what when the James Webb was launched or when it was first putting out information. It's that we're seeing galaxies with 10% the stars of the Milky Way galaxy. Isn't that a fully formed galaxy? And weren't these kind of at redshifts of 10, 11, 12?
Well, what we're seeing are the cores of future galaxies.
Okay.
And so for example, I'm trying to remember, we got a slide here we can show. Okay, our galaxy has a diameter of a little more than 100,000 light years.
Right.
Okay, this galaxy we're looking at, its diameter is about 3,000 light years. So
it's about 3% of what we're looking at.
3% we're looking at. The mass is 400 million times the mass of our star, the sun, compared to 1.2 trillion for our galaxy.
Okay.
But we do know this is going to become a big galaxy because it's the biggest.
So it is a galaxy in some sense, but it's also going to grow much larger.
It's going to grow much larger.
Right. So when you use the term proto-galaxy, that's what you're describing as opposed to I'm a cloud, or it's a cloud that's going to become a galaxy. It does have stars. It's just not fully formed.
For example, the most distant galaxy where we see spiral arms has a redshift of 5.2,
okay,
which corresponds to about 1.5 billion years after the cosmic creation event. Here we're looking at just 291 million years.
Right.
Nevertheless, it's phenomenal that this galaxy is as massive and big as it is that early in the universe. But what was interesting is this spectrometer not only was able to get an accurate measurement of the distance of the galaxy, it was able to determine the composition.
Okay.
So what they saw was an oxygen 3 line. And that means, hey, this galaxy already has elements heavier than hydrogen and helium. Because in Big Bang cosmology, the universe starts off with hydrogen, but by the time the universe is 4 minutes old, a quarter of that hydrogen's fused into helium, and a tiny amount of lithium, very tiny amount. All other elements are made in the furnaces, nuclear furnaces of stars. So here's this galaxy, just 291 million years, or I should say emerging galaxy, just 291 million years after the cosmic creation event, and we can already see an oxygen 3 line.
So this would mean that there's at least a second generation or a single generation of stars has burned and
at least
seeded stuff.
At least some first generation stars have burnt and exploded.
Right.
Because that would explain how you would get oxygen in that particular galaxy. The other piece of evidence they found was they looked at the continuum radiation. That's the radiation between the spectral lines. And they noticed it was redder than what we would anticipate if there were no heavy elements. And
Okay.
so that tells us there's already dust in this galaxy that's actually causing the continuum radiation to look redder than it otherwise would. So this is really the strongest evidence to date that galaxies in the first half billion years of the history of the universe actually have elements heavier than helium, and at significant amounts that we can detect them. So this really ranks as another piece of evidence that the firstborn stars, at least some of them, have to be hundreds of times more massive than our star, the sun.
So make that connection there. Why is that?
Okay. Well, today, because you've got lots of dust in the universe, the biggest star that can possibly form is 150 times the mass of our star, the sun. And that would be incredibly rare. Only a few come in at that mass. Most of them are under 60 times the mass of our star, the sun. But in Big Bang cosmology, the universe begins with only hydrogen, helium, and a trace amount of lithium. And if that's the case, you can actually have stars forming that are much more massive than 150 times the mass of our star, the sun.
Okay.
There isn't the effect of the dust that constrains how big the star could be. And stars burn up in proportion to their mass, and it goes up with almost a fourth power. Exactly, it's a 3.9 power. And what that means is a star 100 times the mass of our star, the sun, will burn up 10,000 times faster.
Okay.
So our star's nuclear furnace can keep the star going for 9 billion years. But if the star is 100 times the mass of the sun, we're not looking at 9 billion years. We're looking at 900,000 years.
You say 10,000 times, yeah, because 10 or 1,000 would be 9 million. So now we're
9 billion,
900,000.
900,000. Okay. And in fact, there's other observations made by the James Webb Space Telescope that tell us some of the firstborn stars had to be more massive than 300, even 500 times the mass of our star, the sun, in which case they're going to be burning up in just a few tens of thousands of years. And when they end up their burning cycle, they explode and basically shower interstellar space with the ashes of their nuclear furnace.
So the fact that we're at 291 million years after the Big Bang, presumably somewhere around 200 million is about when galaxies and stars could start forming in the first place.
Right.
Somewhere in that 91 million years, you've got to have stars that are burning up and exploding so that we can see what we see.
You can see the
and
oxygen.
So that puts a minimum mass of how massive some of these stars have to be. You could have things much more massive because they would burn up faster, but it's got to be at least something on the order of 10 times as massive as the sun.
You
in
either
order
have
to,
to have a
fast.
bunch of stars, say between 1 and 300 times the mass of our star, the sun, or a few between 300 and 1,000.
Gotcha. Okay.
We don't know the answer to that yet.
Right.
Whether you have some that are really extremely massive and you don't need a lot of them to get these ashes,
right.
or you have a whole bunch that are between 100 and 300 times the mass of our star, the sun. But yeah, this is additional evidence that indeed Big Bang cosmology is on track in predicting that some of the firstborn stars indeed will be much more massive than stars we see today, because that's how you can explain why there's an oxygen 3 line, why you're seeing dust and the continuum radiation. And this is only one galaxy. Clearly, to get a more definitive picture of what's going on, we want to discover more galaxies that are within the first half billion years after the cosmic creation event. Again, use this mid-infrared spectrometer in the James Webb to get an accurate measure of what the elemental components of these galaxies are. And people are saying, why can't James Webb do this right away? Notice it took a few years to actually get the telescope time to make, because they had to use several hours of observation on this galaxy to get the spectrum. And even then, when you read the paper, they say, well, we don't know the abundance of this oxygen. We are about 99.5% certain that the oxygen is there, but that means we're 0.05%. This may be spurious. So it's like clearly more observations need to be made. I'm more convinced by the reddening of the continuum, that to me, I think is even a stronger case that indeed there have to be some of these firstborn stars that are very massive to explain this. So, but what I find ironic is that you have young Earth creationists a year ago saying, James Webb is telling us that these stars during the cosmic dawn, the first billion years, they have 4 times too few heavy elements. And this is counter what we expect from most Big Bang models. Therefore, the Big Bang is not correct. Now they're putting the other way. We're finding a galaxy with too many heavy elements. Therefore, the Big Bang is wrong. And it's like you can't have it both ways. And from an astronomical perspective, we're basically, it's kind of what you're discovering about the magnetic field of the Earth. It looks like what's going on during the first billion years of cosmic history is way more complex than what we expected, because we got some of these emerging galaxies that seem to have an overabundance of heavy elements. We got a whole bunch more that have an underabundance. What's really going on here? And is it possible we're getting galaxies with a higher population of hypermassive stars than other galaxies? I suspect that's really the answer, is that, and in our own galaxy, we actually see firstborn stars that are, below the mass of our star, the sun. They've actually been existing for over 13 billion years, but because they've been existing for 13 billion years, they've been polluted by the ashes. But what we can tell is they really were firstborn stars that got polluted during their formation period. Because if a star is, let's say, 1/2 the mass of our star, the sun, it's going to take several 100 million years to form and become a star. And during that time, it's bound to be polluted by the ashes from firstborn stars that are, say, 300 times the mass of our star, the sun, or even 100 times the mass of our star, the sun. So already we know there has to be a range of masses amongst these firstborn stars. Some of them are smaller than 1/2 the mass of our star, the sun. James Webb is telling us some of them probably are 1,000 times the mass of our star, the sun, maybe even more massive. But if we're going to pin down which of the several dozen Big Bang creation models is the correct description of the universe in which we live, we're really going to have to nail down the mass distribution of these firstborn stars. I think that's a 10-year project.
No, that wouldn't surprise me. Yeah. So from an apologetics perspective, what's the, I mean, this sounds callous. What's the use of this? Because at some level, largely in my talking to young Earth creationists, many of them, the science isn't really the driving point there. So having more science that shows Big Bang cosmology, how do you see this being or how would you use this tool? That's, I guess, my question. So.
Well, there's 2 ways I'd like to go with this. Number one, what we're seeing with the James Webb Space Telescope is increasing evidence for the Big Bang creation model that the Bible predicted thousands of years ago. I mean, I've written articles making the point. The Bible doesn't give us all the details of the universe in which we live, but literally thousands of years ago, it explicitly taught 4 fundamental features, what we now refer to as the Big Bang model. So the Bible said it first. It wasn't 20th century astronomers that discovered the Big Bang. You got people like Job and Moses and King David and Jeremiah and Zechariah, Isaiah speaking about the universe in which we live. And so this is giving us additional evidence. The Bible indeed correctly predicted the features of the universe we're now discovering.
So I am just to press a little bit, because I know this would be a question I would have, and well, it is a question I have. How would you respond to the claim? Okay, so if the Bible predicted this, why didn't Christians talk about this until the 20th century, where Big Bang cosmology came about? I mean, for the 1800s, scientists, most Christians seem perfectly content to say the Bible talks about a beginning, but the universe
that's a great
is billions
point,
of years.
Because people said, Hugh, you live in the 21st century, you're applying hindsight to the scriptures. Were there people living before you, before the 20th century, that saw this in the Bible? And the answer is not too many Christians wrote about this, but Jewish theologians did.
Okay.
And so from about 1000 AD to 1200 AD, you got a half a dozen Jewish theologians studying the Old Testament texts and saying, hey, these texts tell us the universe has a beginning that includes the beginning of space and time. It tells us that the universe is expanding from the beginning. It tells us that the laws of physics haven't changed. So they were seeing these Big Bang features and writing about it 1,000 years, 800 years before you've got astronomers in the 20th century saying, hey, our telescope is telling us the universe has these features. So it's not just hindsight. You got people literally centuries ago reading the scriptures and seeing this. I'm a little curious why I don't read in the literature more Christians seeing this. So I've read the Middle Ages Christians. They seem to be focused on other theological issues. The Jewish theologians were very interested in the cosmology, more so than the Christians were. But
no, it's just interesting. I read that because I get what you're saying, and I agree. I think there is evidence for it. And I think, I do wonder how much can you push that the universe is expanding, and that's what Scripture's teaching. But it certainly seems consistent with it. It uses that language, but the idea of immutable laws of physics, of a beginning, those seem pretty straightforward in there. But it's certainly, your explanation makes sense, but it's not the sort of thing that would compel me to think that, this is what Christians all along have thought. But I think I think it's a powerful point that what we see when we look at Scripture long before we ever had the scientific data aligns with what we see in the scientific data.
Even in the early church fathers, which is just right after the formation of the Christian community, they were explicit in writing the universe has a beginning. They're also explicit about a space-time beginning. It was the Jewish theologians that says, hey, Maimonides, for example, wrote about the universe. The Bible tells us we live in an expanding universe. So I don't have any evidence that Christian scholars, and again, we don't have all the literature that these Christian scholars wrote, but we do have extant literature saying at least the Jewish theologians saw these features in the universe, and the Christians certainly saw the point about the beginning and constant laws of physics and the fact that it's a space-time. So they saw 3. The Jewish were seeing 4.
Gotcha.
So, and now we're discovering this. But I think I got a slide here. We can move to the next slide. This is actually a galaxy a little bit closer to us than this most distant galaxy. It's GNZ11. But what's interesting is they actually found a little bit distant from this galaxy a cloud of gas. And that gas was being illuminated by extremely bright stars in the core of this emerging galaxy. And in the emerging galaxy, they can see elements heavier than hydrogen and helium. But in this gas cloud, in the halo of the galaxy, all they see is hydrogen and helium. So it's the one place the James Webb Space Telescope had clearly identified a place in the early universe where all you see are the elements that were formed in the first 4 minutes after the cosmic creation event. And that's a key fundamental prediction of Big Bang cosmology, that before stars form, all you're going to have is hydrogen and helium.
Right.
Here's a gas cloud where there's no stars, but the cloud is illuminated by bright stars in the core of the emerging galaxy so that they can measure the composition in the halo, and all you see is hydrogen and helium. But to make a second point, what I think is exciting about this paper, I see the potential to draw out a lot more design evidence about God carefully designing the universe. I mean, I think of Freeman Dyson. He says, when we look at the universe, we can't avoid the conclusion that the universe knew we human beings were coming. It was step by step fine-tuned to prepare for our entry. And I think what we're seeing with the James Webb is even during the first 500 million years, it looks like things were being fine-tuned, being designed with human beings billions of years later in mind, getting things ready for them. And we look at the universe as being almost 14 billion years old, but as I look at the history of the universe, it seems to me that God was really in a hurry to get things prepared for human beings as fast as possible.
I don't know that God's ever in a hurry, but I get your point. It's like he was working to bring it about
Yeah,
quickly on
he,
our
he,
time
he was
scale. Yeah.
aggressively
Yeah.
creating,
Right.
get everything in line. He could have brought us on later, but he brought us on as soon as the laws of physics would permit. And yeah, he could have done it faster, but we would have needed different laws of physics. So given the laws of physics he chose, and he multiple reasons for those laws of physics, what we're seeing in this paper is God isn't just, twiddling his thumbs. He's very active and aggressive in
Yeah.
getting things ready. And to me, what's going to be exciting is discovering, okay, I suspect that when we get the mass distribution of the firstborn stars, we're going to discover how exquisitely designed they are to get the distribution of stars we need billions of years later to make our existence possible in the universe and to get the kinds of galaxies we need at the right time in the universe. So within 10 years, I'm going to be really thrilled with what
right.
James Webb is discovering. But I think people are unnecessarily being impatient. It's like, why can't James Webb give us all this stuff right now? Well, at those great distances, even the James Webb Space Telescope is extremely challenged to get this kind of information. And that's why they said we want to make sure it's up there for 30 years because I think it's going to take that time to get all the information we want. Well, thank you for joining us today on Stars, Cells, and God. Join the discussion in the comments below. Remember to like this video and to subscribe for more content. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend, and remember, the more we know about science, the more reasons we have to believe in Jesus Christ as Creator, Lord, and Savior.